Everyone. Here's the second half of the review, essentially the second half of the class, the final review from last year. We covered surveys and waste, instrumentation, brachytherapy, and medical events, and then finally DOT shipping and proton therapy. So let's jump into it. Remember that there are designated controlled areas. These are areas that have an active, radiation safety presence. Staff wears dosimeters. You know that there is a potential for radiation exposure and higher levels of radiation exposure, though there are still limits on these areas. But it's generally areas where there's not members of the public who are subject to much, much lower dose limits. So as controlled, as you would think it means, these generally some way that the access is restricted to these areas. You don't have members of the public just walking through the lobbies of the Linac vaults, because that's a restricted area. You would not want that to happen. So remember that these areas have different design goals than an uncontrolled area. That's because you have occupational workers there, so you have higher dose limits. The areas there, though, are designed for pregnant staff, and also just as an ALARA principle of keeping everyone with doses as low as you can, but it also allows for pregnant staff to continue working. So that is something that is now policy, to design to a maximum dose of these levels. Generally, the areas around the Linacs are much lower than even this. They are heavily shielded to a point where you try to keep doses very, very low. But for an uncontrolled area, it's that, member of public, 100 millirem in a year, roughly 50 weeks in a year. So you want to limit to 2 millirem in 1 week. Also no, dose rates over 2 MR at any 1 hour. So other types of posted areas, you can have controlled areas that have known high levels of radiation. So you have these different definitions of radiation area versus high radiation area versus very high radiation area. So they just have different dose thresholds. Remember that very high radiation area is in units of absorbed dose. And that's because if you're in an area that has 500 rad per hour, it is a danger to your life. You're not worried about future risk of cancer. You're worried about, if I stay here for, an hour and I receive 500 rad, there's a chance I'm going to die from that exposure. So that's why they treat it differently than the millirems and the rems. Also, anywhere that has radioactive material use, stored radioactive material, has to be posted with a caution radioactive material sign. And if you walk around the hospital, whenever you get back to the hospital, you'll see that these are posted everywhere, because there's a lot of areas that use radioactive materials. It's also kind of an MSK policy anytime they build out a new place to over sign. So there are some areas that unfortunately are posted without actual use, active use. This is more common in the labs, though. We talked about waste, strategies for minimizing waste. You can actually minimize the waste that you produce. You can get rid of waste. You can pay waste brokers to take it away. But one of the main ways that we get rid of waste is just to let it decay. There's a process of decay and storage that's allowed for isotopes with half-lives under 120 days. Fortunately, most of the isotopes we use in the medical arena are less than 120 days. So we can keep a lot. Sometimes you have contaminants, though, in this waste that has much longer half-lives. So as the short stuff decays away, you end up with a large portion of long-lived stuff, and at some point you usually have to pay someone to get rid of it, because it accumulates faster than it decays, and eventually you'll end up with way too much stuff. We'd say that 10 half-lives is a general good rule of thumb for waste, because waste is generally already at low levels of radioactivity. But if you have something like a couple millicurie source, that 10 half-lives is only going to get you down to a couple of microcuries, which is still radioactive, still detectable, still enough to set off possible portal alarms as this waste makes its way to other facilities before its final destination. So anytime that you actually go to get rid of waste that you've decayed on site, what you have to do is you have to take any shielding away and just survey it with a sensitive meter, the appropriate meter, and it has to be indistinguishable from background. And at that point is the point where you can be comfortable disposing of it as regular waste. You have to take off any signage. You don't want to throw something out with a radioactive symbol, because even if it's no longer radioactive, there's still a chance someone's going to come across it. and they're gonna, kind of freak out. And if it's traced back to your facility, you can get in trouble for that. We talked about instrumentation and just the differing categories of instrumentation. You can, draw a line between different instruments for a number of different ways. One way is the portable first installed instruments. We have a lot of permanently installed portal monitors. Lab equipment isn't permanent, but it stays in one place. And that's contrasted with handheld meters that we use. We take to an area. And even those handheld meters, there's contamination meters versus dose rate meters. So a lot of times you can read out in different units. It's common to read out in activity. So whether that's counts per minute, disintegrations per minute, an area concentration, but then you can have dose rate meters that read out in exposure or, absorbed dose. Exposure is the most common because when you have a gas filled detector, you're technically taking the the exposure rate of that gas. So that is it's one of the easier instruments to use for measuring. When you get into dose or dose equivalent meters, there's some tricky behind the scenes math that they attempt to do, but you have to be a little more skeptical of what the answer that they're giving you or the reading that they're giving you. So another way to divide instruments is passive versus real time. The best example of a passive instrument is a dosimeter. It's measuring something, but it's not giving you any results. It doesn't give you results until you collect it, send it into the vendor, and they issue a report. So that may not be the best in terms of quantifying an active radiation field or getting a real time tally of your dose. That's compared to an ion chamber, which can give you an instantaneous dose rate, or an electronic dosimeter that also has that integrated function where in real time it will show you your dose that you are accumulating, so you can make decisions on the spot as opposed to a dosimeter. Your dosimeter is your permanent record though, so in a situation where you are going into a high radiation field, you would want to wear something that you can read in real time, but also include your dosimeter because that's going to be the true record of what you were exposed to. So we have different detector types. This is for mostly for handhelds, but the same technology is used in fixed machinery as well. But you have the gas-filled detectors. I think we have that gas curve. Yeah, we'll get to that. Okay, so the gas-filled detectors have a number of different voltage ranges that make them behave differently. So we'll get into each of those. Scintillation detectors being that crystal. Scintillation meaning flashes of light. So as the ionizing radiation ionizes this scintillation material, it creates a light, and that's useful for quantifying radiation as well. And then finally, there's other forms. Dosimeters are different technology. Semiconductor detectors can be very small, so those are useful for use in phantoms and such. So a gas field detector is, like the name says, a volume of gas. It has a high voltage across this gas, and that way any ionization of the gas inside the detector creates an ion pair, and that high voltage then pulls those ion pairs in their respective direction, and that gives the behavior of the differing regions on this gas-filled curve. You have the ion chamber region, and remember that's where, do we go into specifics? Yeah. So the ion chamber region, proportional, and then the Geiger region. So the ion chamber region, it doesn't have any multiplication of charge, which what that means is that it's actually tallying the amount of charge that is produced in that detector volume, and that's how it allows to give you, it's able to give you, an instantaneous dose rate, because it's reading that instantaneous charge collection. It's not, little counts or little blips. It's an actual totaling something. You can have pressurized ion chambers that read to lower levels. Think about it, if you stuff more gas atoms into the same volume, it'll give you a higher pressure, but the higher pressure allows you to have a more sensitive instrument. Proportional counters. So these are the midpoint on that, that gas curve, gas detector curve here. And you can see this is, at this point, there's that separation between alpha particles and beta particles. And what this does for a proportional counter is it lets you set the voltage to see just alpha particles or see alpha and beta particles. And so if you can take those two readings, then you can know the number of alpha decays versus the number of beta decays. If you take both measurements, you can, you can subtract away the alpha count from the alpha and beta count and get the beta count. through that means. So that's useful because those two decay types, they have different contamination limits. There's lots of different limits for an alpha versus beta. So there's lots of times where it's useful to know that if you're getting counts in an area, you want to know if those counts are an alpha or a beta, because with something like a GM or even an ion chamber, there's not going to be that discrimination. It's just going to tell you one number, and you're left wondering, what is the cause of those counts. There's other kind of back, workarounds that you can do. Alphas are very easy to shield. So if you have a GM and you're counting a spot of contamination that you don't know what it is, you can then take a piece of paper and put it in the way. And if it's pure betas, your count rate won't change. If there's an alpha component, the alphas will be shielded by that piece of paper. And that also gives you, two count rates that you can figure out. And then your GM is the highest voltage on this region. So that means it's the most sensitive. A GM is very useful for detecting bits of contamination. The problem is all you get is a click. It gives you no information about what is actually there. It just lets you know something is there. And the reason for that is that any ionization event inside the GM, inside that gas volume, it creates a sort of cascade effect, this giant multiplication effect, where essentially every atom inside of the GM is ionized for a brief period. And this is for any ionizing event, whether it's a particle or a photon. It will all get the same response out of this instrument. So all you're given is a count rate, which is useful. It's useful for certain situations, but it is also limiting in a lot of ways. There's also something called dead time with a GM. A GM needs a certain period of time to recover from a count. We're talking about the order of microseconds or less. But if you are in a radiation field or you're surveying, a spot of activity that gives you hundreds of thousands of counts per minute, there's a lot going on in, fractions of a second. So this dead time can actually, artificially lowers your count rate because you're missing counts in that period of time while the detector is recovering. And you can actually get to a point where you completely saturate the meter and it's so overwhelmed with radiation that it doesn't even get that chance to bounce back, and it will just read 0. And that's a dangerous situation because that comes about in very high radiation fields. So that's the last place that you want your instrument to stop working or artificially telling you there's no radiation. So a lot of GMs will have some built-in electronics that prevent that. That's useful. There's also a huge energy dependence with GMs, so you should never trust a dose rate from a GM unless you have a very reliable conversion factor, because the GM can be off by an order of 100 or more. So if you're in a radiation field that's 1 MR per hour, it might read 100 MR per hour, and that's a problem. We have that happen a lot in our office. People calling saying, "Oh my God, there's so much radiation." We go down there and we find that they're using a GM to try to do dose rate. We bring a dose rate meter, and it's it shows that it's off by quite a bit. Then you get into the scintillation detectors. Remember, the scintillation is a crystal detector. It's a special type of crystal that creates those flashes of light. It's generally sodium iodide with some sort of phosphor doping in it. It's a thallium that somehow helps maximize that light production. So behind that is a photomultiplier too that takes that little blip of light and actually creates an electric signal from it. So that intensity of that light is actually proportional to the energy. So that's how you have sodium iodide detectors that can actually measure the amount of radiation, the energy of the radiation, not just that it's there or not there, but the actual energy of the radiation, which lets you ID certain isotopes. If you find a mystery bag of garbage that's radioactive, you have sodium iodide detectors that can tell you the energy coming off of that. And then from there, you can make a pretty educated guess as to what is in the bag. We also have lab systems. Gamma counter is based off of a sodium iodide detector, but instead of just being, a circular crystal, it's an actual well. So you drop samples inside of that crystal. So you get a much better efficiency. You get much better geometry. So you'll have much higher efficiencies with these machines. This is a liquid scintillation counter, which similar to a scintillation crystal. The scintillation medium is actually a liquid that surrounds the sample. So if you have a very low energy sample like tritium, it has direct contact with that scintillation medium. And that's actually the only way that you can count tritium, because tritium is not able to get the beta particles that it releases are so low energy that it actually can't get into any sort of detection volume. You need to have direct contact in order to see those betas. So that's why liquid scintillation is very important, especially for labs using tritium. We have bioassays at our hospital. Fortunately, the only one we have to do is thyroid counting. So you have researchers that are working with radioactive iodine. You have a lot of clinicians that use radioactive iodine in therapy, use huge amounts of radioiodine, sometimes up to a curie or more. So we want to monitor these people because there's chances iodine just chemically is kind of volatile. So that means that you can have a solid iodine source that some of that iodine will actually, vaporize off of it. And that's a potential hazard for breathing it in. So if you're using loose forms of iodine, there's a potential that people will have an uptake of iodine. So we take measurements of someone's thyroid before they do this therapy and then after. And with that, you can see if that count rate in their thyroid has gone up. And then you can use that elevated count rate to figure out a quantity of iodine that is in the thyroid. And from there, you can assign a dose. If you know exactly when, like if it comes from a therapy, you have a nurse or a physician that did a therapy on a certain day, and then they come a couple of days later and they have a positive uptake. We can say, okay, well, when did you work with iodine? And if it was 3 days ago, we can use what are known as intake retention functions to say, okay, well, 3 days later, there was this much activity in your thyroid. We know that the thyroid clears iodine generally at this rate for the average person. And then so we can back that up 3 days and say, okay, well, this is how much that you actually ingested. And from there, we can assign a dose to it. That's an estimate. All measurements in radiation safety and health physics are estimates. 10%, plus or minus 10% is considered a very good measurement. So that's kind of what you have to do. It's the best you have. So that's what we work with. So we have dosimeters. Dosimeters are, a very important piece of instrumentation that's used in the hospital. They have a lot of technology in a little dosimeter. They have different filters that let you know the energy of the radiation, whether it's a deep dose, shallow dose, lens of the eye dose, the type of radiation. The RT badges have a neutron sensitive component because you guys are working around neutron producing equipment. So we need to be able to see if for some reason the neutrons are getting through the neutron shielding. That's very important for us to know if that was happening. So all instruments have a certain level of efficiency. That's essentially just how good they are at seeing what's there, how many, disintegrations per minute are actually happening versus the counts per minute that the instrument is getting. And you can see that a lot of instruments have, the efficiency curves in comparison to energy. Now this is for a handheld. The 44.9 is one of those pancake GMs. It makes sense that it caps out at 50% because if you think about it, you have a flat face of a detector up against the source. Half of the decays of that source are going in the other direction. So there's really no way that you're going to detect those unless you have a detector that surrounds the sample. But most handheld detectors are limited to seeing at most 50% of the source. So that's why you see that a lot of these curves climb to that 50% mark if they're talking about a 4 pi geometry. And that means that like a 360 degree, impression of the source, at best you're getting 50% because 50% of it's going the other way. Yeah, so the calculation for efficiency is essentially just the amount of counts you get per actual disintegrations present. This efficiency for dose rate meters is something that is, calculated during the calibration. So this is something that we don't have to do on our own. The instrument kind of does it for us. But essentially, those instruments also come down to count rate meters in some regard. That there's some sort of MR per hour in relation to the count and the charge collection that happens in the actual chamber of the ion, the chamber of the ion chamber. So getting away from instruments, we touched on brachytherapy a little bit. We mentioned that, there's differing strategies for brachytherapy. You have permanent implants versus temporary implants. Some temporary implants are for a couple of days. Some temporary implants are for seconds or minutes at most. So you have the temporary versus permanent. You also have the different types of energies of the sources being used. So one of the biggest brachytherapy procedures we have, one of the most common, is a prostate seed implant. You can see all the seeds that have been inserted into this person's prostate. They're low dose radiation. Each individual seed is a millicurie or two, but you're putting 50 to 90 seeds in there. But it's still considered low dose and low energy. Usually it's iodine 125 or palladium 103. Those are both very low energy, which is useful for the prostate because that means a lot of this radiation doesn't get too far outside of the seed. It doesn't, reach depths of tissue outside of the seed because you have a lot of sensitive structures in that area. You don't want to give a ton of dose to the bladder, just other anatomy there that can be harmed by this radiation. So that's why they use so many seeds, and they have computer programs that figure out the exact configuration for how you want to put these seeds in there to give the maximum dose to the tissue that is, the diseased tissue, and spare healthy dose. We've started to use seeds more and more in lungs and brain cases as well, but they're generally all low dose rate and low energy permanent implants. They're in there until they decay away. Sometimes this therapy will be supplemented with external beam just to deliver, an extra little bit of dose to that, or extra lot of bit of dose to the prostate. So you have temporary low dose rate, low energy implants, and these are generally eye plaque implants. You sew a little plaque holder with a small amount of shielding in it onto the eye, and that little metal backing prevents the radiation from going elsewhere. That's good. Minimize the radiation to the person's brain, which is important. But this is a temporary implant. They are kept in the hospital for a couple of days. They're usually sedated because, from what I understand, it's a very uncomfortable procedure to have this thing stitched to your eye. But it's also so these people don't fail to come back. You don't want to let somebody walk out the door with a source stitched to their eye, because if they don't come back, they could permanently destroy their eye and cause serious harm. It's also the care factor of being able to deliver care to these people when they're on site as well. There's low dose rate, high energy sources. We don't use these as much in our facility, but there's cesium implants. The benefit of these being cesium is very long-lived, very stable radioactive element, which means that it's a predictable decay. So from a cost perspective, it's easy just to use these sources, re-sterilize, use them again and again and again. But because they're high energy, that means that you're going to give a lot of dose to healthy tissue, which is why I think they've, sort of fallen out of favor. And then that brings us to the high dose rate treatments. So these are the HDR units, also known as remote afterloaders. These are the brachytherapy procedures that have, a 10 curie source, a 9 curie source. And so that's a huge amount of activity compared to, a couple millicurie seed. So these are therapies where, the source is put in for a brief amount of time and then taken out. You need a reliable way to make sure that source gets positioned exactly where you want it. That comes down to the length of the catheter, the retraction length of the actual seed that comes out of the machine itself. But just because it's such a high dose rate procedure, high activity procedure, these need to be done in very specialized shielded rooms. They need to have a lot of safety precautions. There needs to be someone outside that room that's ready to jump in there and pull the seed out of the patient if it fails to retract on its own. We have in these rooms, we have what's called the doghouse, which is essentially a small shielded room inside of a large shielded room. So if this, this unit was using to be treating a patient and suddenly it didn't retract, there's emergency steps in place to go in there, retract the source, try to wind it back into the machine by itself manually. But if that doesn't happen, then you just take the whole thing, throw it in this other shielded room, get the patient off the table, and just get out of there. We actually had a situation similar to that somewhat recently. Thankfully, the physicists handled it very well. They were right there. They were ready to do what they needed to do, and it actually saved the patient a ton of dose, The physicists themselves did not get a lot of dose. They were very quick in what they were doing. And fortunately, it avoided what could have been a much bigger issue. So all these procedures really come down to the energy of the isotope in use. The dose rate also comes into play, but the energy is what dominates in terms of shielding. You could have a therapeutic dose of I-125 that can be inside of a small lead envelope, and that's enough to shield it, versus, cobalt-60 needs quite a lot of shielding. That's not really for brachytherapy. That'd be more of a teletherapy thing. But even something like iridium requires a bit more shielding than those low energy stuff. We get a lot of these sources from outside vendors. They come with calibration certificates, but we always order a couple of extra calibration seeds, and this lets our brachytherapy group do calibrations on the seeds themselves. It's a second check on these sources. Just because the vendor says that it's a certain activity and a certain seed strength, it's probably prudent to check it yourself. So that's what we do, because any one person is capable of making a mistake. If you have a second person looking over their shoulder, checking their work, then there's much less likely that this will be able to harm somebody. There's a huge task of inventory when you're dealing with patients that are receiving something like 60, 70 seeds. You have to really be careful that these seeds don't go missing, because even a single seed going missing is reportable to the city, and that will result in an inspection. They'll come around and say, okay, well, let me look at your program. You're losing seeds. Let's find out why. And the unfortunate thing is that, we lose very few seeds, considering, in a single day, you could have 4 prostate implants. So that might be a couple hundred seeds that are used. So if you lose 1 seed in a year, that's 1 out of thousands of seeds, but it's still enough to initiate an inspection if you do lose it and can't find it. So you have to report it to the city. So inventory is very important. There's an active inventory happening while the seeds are being implanted. As soon as the case is over, the brachytherapy physicist goes next door, takes a fluoroscopic image of the remaining cartridges to count the seeds that are remaining, and make sure that agrees with the amount of seeds that were prescribed and hopefully implanted. And then that's a check that allows rapid action in case one of the seeds is missing. The first thing to do is they call us. We'll come down with instruments, and then they start looking. They call us, then they start looking themselves. And very often we'll get a call. We'll grab our instruments. We'll head down, and by the time we get down there, they've already found the seed. We're fine with that, because we want to be known as soon as possible. ORs are, there's people coming and going all throughout these cases. So it's not unheard of for a seed to fall like into someone's shoe, into a cuff in a pant. There's just ways that these seeds can walk because they're so small. So the sooner we can get down there, the sooner we can start surveying people, the less likely the seed actually gets far away from the room. Any sources that are used regularly that are not in storage need to be leak tested, not to exceed 6 months. So at least every 6 months. And you want to be able to detect down to 11,000 DPM or 5 nanocuries. Fortunately, a lot of the brachytherapy seeds that we have are used very rapidly or sent back to the vendor. So we don't have to do wipe tests on those sources, but we do have a lot of other sources, like reference sources, that are kicking around, where we do have to perform the surveys. You also want to, after something like HDR treatment, it's very important to do a survey to make sure that that source is out of the patient. There was a case in Pennsylvania, where an HDR source actually broke off inside of the patient, and there was no survey done. That patient went back to their nursing home, irradiated a lot of fellow nursing home residents, irradiated a lot of staff, and ultimately died from her personal exposure because the source was left inside of her, and it was a minimum 5 or more curie source that was just irradiating her nonstop because it was physically inside of her. So that's like an absolute disaster scenario that could have been stopped with something as simple as a survey. Fortunately, it was not done, but that made it so it is absolute policy now to survey after every single patient. We actually have fixed monitors inside of the HDR suites. So even if you don't have a handheld monitor, there are area monitors with displays on the outside of the vault that shows that the source is either in or out. So there's lots of fail safes to prevent something like that from happening. Patient release is, it's different for every therapy, every isotope, every activity used in therapies. But really, the one dictate from regulations is that you can release a patient as long as no member of the public gets over 500 millirem from the release of that patient. And so this is a little different than that member of the public, because it's assumed that 500 millirem will be going to a family member. They're going to be the ones that are going to get the most dose from a patient leaving a facility and going home. So this is deemed acceptable to have this higher than 100 millirem, because the thought being that there's a big benefit to the patient. There may be a benefit to the family having their patient member home. So we have to make sure that they're still, at that point, they're still not going to get more than 500 millirem, and that if there is anybody that's going to get expected to get more than 100 millirem, then we have to give detailed instructions to the patient to make sure that they know how to keep doses to everybody else as low as you can. So I mentioned this is what we do, the licensee calculating dose to figure out if there's any risk of people being overexposed. But there's other ways to do it. They're generally much more restricting. You can do it based off of activity administered alone. It says that if you administer more than 33 millicuries of iodine 131 to somebody, they have to stay in house. So we give therapies of 200 or more millicuries where we let the patient leave. But that's because we've calculated dose and given very specific instructions for how to minimize dose to others. You can also just go by a dose rate. You can take a reading after a therapy and go off of that and wait for that to decay down low enough for the patient to leave. This is less restricting because the activity that's in a patient will be shielded somewhat by the patient's tissues themselves. So it's useful, or so the activity doesn't correspond to the dose rate of an open source, because the patient is attenuating the radiation. There's also biological decay. The patient is, in some situations, urinating out a large amount of this radioactivity, so they'll decay away much faster than just the initial activity treated. But we use this method for most of our patients just because it is the least restricting. So we talked about medical events and what exactly is a medical event. A recordable medical event, something you write down, versus a reportable medical event, something you call up your regulator and let them know. You sort of come clean on a mistake that was made. So in order to know if something was done incorrectly, you need to have some sort of target in mind. And that's where this written directive comes into play. It's essentially a prescription for dose. It's a prescription for a radiation oncology procedure. You want to deliver this much dose to this tissue for this patient, and then needs to be signed off by an AU, who is an authorized user. That's somebody that has been approved by the city to do these therapies. They have the appropriate training and experience, or the appropriate boards and the appropriate time practicing to reliably write these written directives. And that's what in theory should be the person that is ordering these therapies. So we have to know what a medical event is. It's important for you guys to know what a medical event is, because you may be one of the first people to realize that something went wrong. So it's important to know the steps to take if you do suspect that something went wrong. And so a medical event is defined as, using the wrong radiopharmaceutical, or just essentially the wrong radiation type or radioisotope. It can be used on a different person, a different route of administration, different area of the body, or just a different source. All those are defined as medical events. And you need to have also, the diagnostic therapy be off by plus or minus 50%, or just the total activity off by 10% or more, and 50% of a fraction for an individual fraction, whether external beam, HDR. So if you identify something like this, really the first thing you do is call Larry, Larry Dower, the RSO. I think Jared Pastrana, I think she's still the head of the regional network for Rad could be off on that. And also just the AU, the prescribing physician for the treatment, just to get some clarification before you make any moves. You want to get people together to see if it really is something that is a medical event, if it meets these thresholds, or further, if it's a reportable medical event, something that we need to alert the city to. So you'll see that there's a lot of the same language, a lot of the same percentages, except the total treatment has to be off by plus or minus 20%. And very important, probably the most important, is that it also needs to result in a dose to an organ of over 50 rem or a whole body of 5 rem. So that means that you need to figure out how much dose this mistake is going to give this person. Because a lot of times, especially for diagnostic mistakes, a lot of times you will have a mistake that doesn't reach these thresholds, which means that it's a medical event. You investigate it, you write a file on it, you tuck it away, and then you get prepared to show an inspector if they ask for it. But you don't have to outwardly report it. So you may avoid that reactionary inspection that could be a real pain because, or worse, you don't want to report something that actually didn't need to be reported, and then you cause a lot of pain on yourself for no real reason. So it's important to get a bunch of people together to really look at if it needs to be reported or not before you report anything yourself. So we talked about shipping. We'll go over a quick refresher on that. Remember that the DOT handles all forms of dangerous goods shipping. Radioactive materials is just class 7, one of many. You can have materials that are both radioactive and explosive gases. So that gets really, really complicated really quickly. But thankfully, most of what we do is just radioactive. Remember that there needs to be training for anybody involved in the process. So that training is supposed to be commensurate with your involvement. So if you're, a FedEx driver, you should have some training if you're transporting these materials, but you probably don't need to know detailed information about specific isotopes and such. You just need to know that what are the emergency procedures if I'm in a car accident, if my truck catches on fire. I need to have certain paperwork with me in the cab. I need to be the representative to the first responders. So everyone has a role to play in it. And some people have a more higher level of responsibility than others. So remember that dangerous good package is actually the entire contents of the package. The package itself, it's what's inside, it's the packing materials, the paperwork that goes with it, all the markings and labels on the package, that it's in its entirety makes up a dangerous goods package. Remember that the label is a very specific marking. It's a diamond-shaped marking that tells a couple of very important pieces of information. It tells the isotope, tells the activity of the isotope, and it tells the dose rate at a meter. And those are 3 things that most people, you would want to know if you're dealing with a radioactive package. So that's important that everyone in that process understands what the label means. If you're dealing with a source that has a high amount of external radiation, you may be required to placard the actual vehicle that is transporting it. In other words, other markings, anything else that's on the package is considered a marking. That would be, the to from address, the UN number, really anything. So the way the hierarchy of shipping goes is you just have to, it's really trying to quantify the hazard level of the isotope. So isotopes all have different levels for meeting whether it's exempt, limited quantity, type A or type B. But really it just tries to gauge the relative risk of that isotope being in transport. If there was to be an accident, how dangerous is that isotope if it was in a fire, if it was, if it leaked from its confinement, how dangerous is it? And that's really what dictates the level of shipping precaution that is needed in these 3 or these 4 different classifications. So that exempt is really, it's just its own table of all the isotopes. And if you do not have above the activity listed, it's exempt. It's not considered radioactive in the eyes of the DOT. So you ship it like you'd ship anything else. These activities are generally pretty low. So it's not common that you get by using an exempt. Tritium is one exception. It's pretty high, but that's because it's really not huge hazard until you get into higher activities. And remember that everything else past those exempt values is based off of these A1 or A2 values. And that is its own table of activities that you have to look up. So the A1 or A2 value, A1 is for special form sources. Remember that we don't have a lot of those. Those are sources that are pretty much tested to make sure that they're tested to make sure they pretty much will never leak. You can't say never, but they are very durable sources compared to just regular sealed sources that are also supposed to not leak, but they are much more liable to leak because they are not tested as rigorously as special form. But since we have very few special form sources, we very commonly use the A2 value. So you'll see that these activities are much higher than that exempt level, but the A2 value itself represents that line between a type A shipment and a type B shipment. Remember that you got to do these confusing calculations, whether it's a liquid or a solid, and from there you gotta you have the A2 value. But if it's a liquid, it's 10,000 times less than the A2 value, and if it's solid, it's 1,000 times less. So that really marks the bottom of that limited quantity, this marks the line between limited quantity and type A package. So just because it's an A2 value, it doesn't mean that it's that line. It's the line between type A and type B. It's these values that are the line between limited quantity and type A. So that's the activity. There's also that external radiation level concern. So something that is low activity but still has a high dose rate can sometimes push it up into that type A range, even though your activity is low. This is common for a lot of PET isotopes because they're releasing a lot of high energy photons, so they're difficult to shield, which means that they'll have a higher dose rate. So for limited quantity accepted package, that means that you don't need to use any specially tested designated packaging. You just have to use a strong, good shaped box. The dose rate is pretty limiting, that 0.5. One strategy is if you're close to that 0.5 and you're below the activity, you can just use a bigger box. You get that benefit of distance, and that's a pretty easy way to make sure that you can stay within this limited quantity range. Not having to go to the type A range where you have to do a lot more paperwork. You have to jump through a lot more hoops in order to get that package shipped. And that brings us to the type A. So this is for activities that are above that, A2 divided by 10,000 for liquids, A2 divided by 1,000 for solids. And this is where you can actually have pretty high dose rates on a package. So remember that there's the white 1, yellow 2, and yellow 3. Those are the 3 different labels for a type A package. Labels being these 3 labels that show nuclide, the activity, and the TI, which is the transport index. Transport index being the dose rate at 1 meter from the package. So type A package, this is the type of packaging that is very heavily tested to make sure that it's not going to be damaged by being stuck outside in a rainstorm, having things dropped on it, having heavy things stacked on it, having it itself be dropped from a large height. These are tested to make sure that the source doesn't leak from this sort of damage, that the shielding doesn't come open and expose the source. Those are the main concerns for a type A package. So that's what all those tests are designed to make sure that it won't happen. But it's expensive. It's expensive to have a type A package certified. So a lot of times we just rely on the vendor reusing the same package, assuming it's in good shape. But one thing we have to get from the vendor is that certification showing that package has been tested to be durable. The labels, the dose limits. For type A, you need a very specific shipping paper that has a lot of information written a very specific way. This line right here is exactly how it needs to be written. If you deviate at all, there's a good chance it'll be sent back to you. So that's where shipping gets a little bit tedious, is that you need to really make sure that you have everything very by the book, by the regulation, or else it will get sent back. So remember, to get that A2 value is that line between type A and type B. So once you get to the type B range, this means that you have a very high activity source. It prevents a very large hazard. So you need to have a very, very robust, secure transportation mechanism. And that's a type B container, which is even more heavily certified than type A. I think you can look up YouTube videos and see these things, being involved in mock train wrecks and stuff, just to really imitate kind of the worst of what these can experience. There's not a lot of type B containers that exist because they're not used as often. We had to rent one recently to get rid of one of our radiators. You don't really own one because they could be, they could cost millions of dollars to get the certification, just the physically what they're made up of. So you have to kind of reserve time on them. We waited for over a year before we were able to get this this mechanism that would allowed us to ship off that irradiator. This is actually removal of a cobalt source that happened a while ago. The irradiator was much more recent. But yeah, so type B is really the top of the top in terms of activity levels and such. Empty packaging, confusingly enough, has its own designation. It's not just empty, but it is UN 29.8 Class 7 empty, which essentially means that it allows you to have some sort of internal contamination. So if you're going to be shipping sources back and forth, some isotopes more than others just seem to work their way outside of confinement. I know iodine is one that I think it does actually to a certain extent kind of slowly bleed through glass. So if you have a lead pig that's being used frequently, it's not uncommon for it to have internal contamination. So you can take a survey, you can quantify this contamination, and if it's below the inner limits for contamination, you can send it as empty. There's not a lot that you have to do to send something as empty. It's less restrictive than type A, limited quantity, things like that. But it is its own designation. Now, if you have a package that doesn't have contamination, you're just sending back an empty lead pig, you can actually send it back as a normal empty package. You don't have to do anything in terms of a dangerous good package. But this designation lets you have that contamination present. On the other side, the flip side of receiving packages, you're supposed to survey a package within 3 hours of receiving it, both for contamination and if there's any visible damage on the package for external dose rate. The thought there being that if there is trauma and damage to the package, the shielding may have come loose and you can be subject to much higher dose rates than when the package started its journey. So they want to make sure one of the first things you do when you get a damaged package is take out a dose rate meter and make sure you're not dealing with something that has gone up in dose rate very rapidly. You also are expected to do a contamination survey of the package. So the person who sends it is supposed to do this, and the person who receives it does it. And you hope that it didn't either leak or pick up contamination along the way. If it does, it can reach level where it's reportable. And unfortunately, when you report something like this, the common response is an inspection. Even though you didn't send that package, you're only receiving it and saying that it had contamination. We've had it in the past, a situation where we had a source that leaked, and we called the New York City regulators, and they came and they inspected our facility. And that's, we have nothing to hide, but it seems strange that we would be the focus of that when we only received the package. And then finally, we did a very brief section on proton therapy. Don't have a ton to add on proton therapy. Remember, it's just that whole concept of the Bragg peak. The behavior of protons being that they give a small entrance dose until they lose a lot of their energy. Then right before they lose pretty much all their energy, there's a peak of energy delivery, a very focused peak that helps you avoid exit dose compared to a typical photon treatment. It's actually such a sharp peak that they have to have a method of what they call an energy degrader. So you have a proton beam and you want in real time to modify the energy of that proton beam in order to hit different depths. And that's where you get this spread out Bragg peak, is different energies of proton beams that can reach a certain depth in tissue. And also the proton beams have much less beam spread over the same amount of distance compared to like a photon beam or an X-ray beam. And that's because they're more massive particles. They tend to be less deviated from their path. So that also gives you that sort of pencil beam scanning, where if you can control the depth and you can very accurately control the left-right movement, that means that you can very accurately paint, a tumor region. And the thought being, it gives you another benefit of sparing healthy tissue. The problem being that not a ton of research has panned out showing huge improvements in overall outcome from proton therapy. So it's had trouble taking off as a desired therapeutic strategy. You really need to show those improvements before insurance will start covering the procedure, before it really gets mainstream adoption. But kind of a chicken and egg thing, because you need to have these facilities to do the research to show that there's an improvement. So facilities are being built. We have the one up in Harlem being built. I believe it's going to be open soon, if it's not already open. So that will hopefully, that's exciting. That we'll see. We'll get some more information, a little more local information in terms of our own patients going to this thing at greater levels. So I'm really interested to see how that pans out. But that is the end of the final review. So that's all that I have. If there are any specific questions that you guys have regarding any of this stuff, feel free to reach out. You guys got my email address, and I would be happy to clarify anything you guys need. But other than that, best of luck. Sorry that the end of the year is probably not going the way that you guys dreamed it would, but I hope you guys are able to persevere through it, and best of luck with the boards. Take care, guys.